Welcome, everybody. This is going to be a deep dive on routing on AWS. Hope you brought your scuba gear. My name is Tom. Here's Ankit. Both of us are principal solution architects focusing on networking. So we spend a lot of time with customers like yourself, talking about architectures, talking about designs, and we're going to share some of those with you today. On the agenda, we're going to start from some fundamentals, talk about routing building blocks, and then move on to giving you examples of different routing configurations. Going from a single VPC all the way to multi-region, multi-VPC scenarios. Just know that we had to cherry pick the scenarios that we thought are the most useful. It's really hard to fit all of the scenarios in a 1-hour session. From a level point of view, this is a 300 level, which means advanced. Just be aware that this number is an average. So we'll start from maybe more fundamental topics and progressively go deeper and deeper, and in the end, we might even give you some code samples and kind of a little bit of an expert level overview. If you want to find out about some of the other networking constructs, so if you want to dive into foundations, there was a session NET318, and then for deeper dive on global connectivity, NET318, and then NET301, I think, which is happening later today in an hour in the Venetian. All right. Let's start with fundamentals, building blocks. So the first thing we're going to talk about is what is a route. This is a session about routing, so let's set the basics. A route is a destination, so where we're trying to go to, and then how do we get there. In terms of networking, it means there's going to be some network that you're trying to get to, and then some path, next hop, that will take you there. So an example here is an IPv4 route, and then the next hop is an interface, or an IPv6 route, and then the next hop to get us to this destination would be some v6 IP address. Now, when we look at any routing solution out there, so this is not specific to AWS, they will usually have two routing databases. There's going to be a routing information base and then a forwarding information base. And I'm just going to show you an example of what do they do and how they differ. So let's say we have a router. It has a couple of interfaces, A and B, to network 1010. Those get put into the routing information base. We then have another interface, interface C, maybe network 1020. That also goes into the routing information base. Then the router goes through all the routes in the routing information base and selects the best routes to a particular destination. So you can see that for some reason, interface A got selected as the best path. So ultimately, routing information base is all of the routes that a routing component is aware of. And then the forwarding information base are the best paths to any given destination that the router is selected. Now, within AWS, when you're looking at the AWS networking components, we are showing you the forwarding information base. So even though there might be multiple paths to the same destination, when you look at the route table on any given solution, you'll see the forwarding information base and only the best route. And you'll see how that makes sense in some examples in a second. From the components that we're going to talk about today, we're going to look at the virtual data center, so a VPC with route tables inside of that VPC. For global connectivity, we'll talk about transit gateway. Transit gateway is a logical regional router, a distributed system, not a single point of failure, that allows you to connect 1,000 VPCs within the regions. And then we'll look at Cloud One. Cloud One, you can think about it as a collection of managed transit gateways deployed globally that you can manage through a single policy and allows for dynamic routing between regions. From a hybrid connectivity, we'll look at AWS Direct Connect, which is our fiber connectivity to AWS, and then a site-to-site VPN, kind of more traditional IPsec VPN tunnel managed by AWS. We'll also touch on software-defined wide area networks, SD-WAN, but we don't have a native solution. I'll show you how you integrate a third-party solution into AWS. Okay, so when you're looking at AWS routing components, there will be 3 common route types that you will experience. There will be static routes. So these are the routes that you, as an administrator, you configure them manually, pointing to a particular destination. Propagated routes. These are routes that will appear in the route table automatically based on the existence of a route somewhere else. So maybe there's a VPC somewhere, and you're automatically propagating the CIDR ranges of that VPC into some route table. And I'll show you some examples in a second. And finally, dynamic routes. So when we see dynamic routes within AWS, that usually means Border Gateway Protocol, BGP, which is a standard protocol for exchanging routing information out on the internet as well. You have two peers, they connect over TCP, they exchange their routing databases. Now, if you receive the same route from multiple places or from multiple different ways, maybe static routes, propagated routes, as well as dynamic, what is going to be the order of preference? So we will always prefer static routes over any other routes that a networking component will see, then propagated routes, and then finally dynamic routes. Now, there's one exception there. This applies if you have the same routes. If one of those routes is more specific, so maybe if you have a dynamic route that is more specific than a static route you configured, the dynamic route is going to be preferred over the static route. Now, we can also have a scenario that within propagated routes, we might receive the same route from multiple different sources. And there will be tiebreakers for propagated routes, and this could be based on maybe the route is coming from a VPC, and that's more preferred over the route coming over Direct Connect, and that is more preferred over the same route coming over VPN. This will depend on the networking solution you're using, and I'll show you some examples as well. Finally, for dynamic routing, because it's using BGP, so if we're seeing the same routes coming in over BGP, we can use standard attributes to manipulate those routes, local preference, ASPath. I'm not going to explain what they are right now. Ankit is going to show you some examples in the second half and explain how they're being used. All right, so we're done with foundations. Let's start going through some examples. And I'm going to start with a single VPC and single region. But before I go into a single VPC, I want to do a little bit of a comparison between the on-premise environments and AWS cloud networking. So if this is a router, say it's an on-premise router, it might have a number of interfaces going to different subnets and then hosts on the other end of that subnet. Pretty simple. So subnet A, B, C, and D. If we translate that into AWS, into a VPC, instead of those hosts, we would see EC2 instances, our virtual machines, or some container environments, even Lambda functions. We also have the construct of subnets. So we would have subnets in AWS. And then they usually would be wrapped inside of a VPC construct. So VPC will have a CIDR range encompassing all of the subnets inside. And I'm showing you an example here with IPv4. A VPC also supports IPv6, so you can have dual stack resources or even v6 only resources. But you see here this implicit router in the middle of the VPC. Right? This router has a route table that's the main route table that everybody is using by default. And in this route table, you see there's going to be two entries. The entries are matching the VPC CIDR ranges, and they're showing next hop as local. So ultimately, with this main or default route table, everyone can talk to everybody else by default. So the question you might have is, if everybody can talk to everybody inside the VPC, why do we even need subnets in the first place? Right? Maybe you just need one big subnet and use security groups to control traffic. So the reasons why you need subnets, number one is subnets are an availability zone construct, whereas the VPC spans multiple AZs. VPC is regional. So if you want to deploy resources in different AZs, you have to use separate subnets for each AZ. The other benefit of subnets is you can create network access control lists, effectively ACLs, around each individual subnet and control traffic in and out of it. And then finally, the thing that we're going to spend most of the time on today is you can actually create additional route tables and control routing on a per subnet basis. Okay, so let's go through an example of how that looks like. In this scenario, subnets B and D are completely private. So we have resources in those subnets that shouldn't be reachable from the internet, but we want to give them connectivity out to the internet, kind of like a one-way door. They should be able to talk to things on the internet, download updates, but nothing should be able to reach them. We need an internet gateway, so that will allow traffic to go out from the VPC, but it also allows traffic to come in. For IPv6, it's a pretty simple solution. We can set up an egress-only internet gateway. That allows IPv6 addressed resources to only communicate out and nothing can come to them. So v6 is covered with this egress-only internet gateway. But let's focus on IPv4 and how routing per subnet can help us achieve what we want here. So we will deploy a NAT gateway in subnets A and C, those NAT gateways will have direct connectivity to and from the internet. They will allow traffic out, but if you try to connect to a NAT gateway from the outside world, your traffic is going to get dropped. And then we will set up routing individually for each different subnet by creating separate route tables and associating those with the subnet. So for subnet B, we have a default route for IPv4 pointing through NAT gateway 1. And for subnet D, we have a different route table controlling traffic in that subnet pointing to NAT gateway 2. And you'll see that through the rest of the session that the name of the game here is to keep your traffic zonal. You don't want to be bouncing traffic across AZs. There's cost associated with that. There's additional latency. So if you can, keep your traffic zonal. And you can do that with different route tables. So you have the same destination network, the default route, but it's different next hop. NAT gateway 1 or NAT gateway 2. Then for the NAT gateway subnets, you can just share the same route table with a route out to the internet, and off you go. Now, some more advanced constructs related to routing inside the VPC are called ingress routing and more specific routing. Ingress routing is a way for us to effectively redirect traffic coming into the VPC from an internet gateway or a virtual private gateway into a network function. And by the way, every time you hear me say network function, it usually means a firewall, but it could be something else, but typically it's a firewall, some next generation firewall appliance or AWS managed firewall. More specific routing, on the other hand, allows you to do a similar thing, also redirect traffic, but this time not traffic coming in from the gateways, but traffic going between two different subnets in the VPC. So overriding that local route behavior. And I'm going to show you examples, because it's much easier to understand with examples. So we're back to our original scenario. We're changing things a little bit. So the EC2 instances at the bottom now will have public IP addresses, so they will be reachable via the internet gateway directly from the internet. But we don't want that traffic to hit those EC2 instances directly. We want to redirect it through some kind of network function. In this example, I'm using AWS Network Firewall. Again, this could be your favorite third-party vendor of your choice that you bring into AWS. Then we create a route table and associate that route table with the internet gateway. Inside of this route table, we see still the local routes. So those local routes are always there. But we're adding two additional routes, saying that if you happen to be going to subnet B or subnet D, you should be going to a security appliance first. And that will redirect traffic coming in through the internet gateway that would normally be sent towards subnet B on D towards those firewalls. Only after inspection, we can use the local routing from the firewall layer back to the EC2 instances. So that's traffic coming in. On the way out, we will also need to use different route tables for different subnets. So for subnet B, we want to make sure that returning traffic is going out through firewall 1. And for subnet D, returning traffic is going to go through firewall 2. Again, keeping traffic zonal. Okay. Now, more specific routing. We don't need gateways, so more specific routing is going to influence traffic that's within the VPC. And what we're going to do is traffic going from subnet A to subnet C should go through the firewall in subnet B. Normally, you wouldn't be able to do that without more specific routing. The local route will take over and allow those EC2 instances to communicate directly. Now, so what you need to do is add an additional route that's going to be more specific than the range of the VPC. Subnet C, traffic to subnet C should go via the network firewall. Once you're in the subnet of network firewall, that route table doesn't matter. It's just a local route. You're getting clean traffic. And then after inspection, you're hitting subnet C. And then you need to make sure that return traffic is also configured correctly so that traffic goes back the same way. Now, throughout this session, we're going to show you some of these pro tips that are little hints and tips of what is useful to think about when you're looking at these designs. So in this example, the more specific routes, they can't be just any routes that you just think of. They have to be the subnet CIDR ranges or the VPC CIDR range. Okay. So there's one problem with static routing that I haven't told you about yet, is that within AWS, when you set up a static route, there is no next hop health awareness. So we don't know when we configure static routes to some network interface that something behind that network interface won't go down. On-premise, you would be using things like VRRP, HSRP, kind of virtual IP addresses to solve that problem. That doesn't exist on AWS. So what do? Well, option number one is you target resources that are already highly available within AWS. So these could be things like NAT gateway, network firewall, transit gateway. These appear inside your VPC as a single network interface, but behind that, there's multiple components. Or the other option, for self-hosted solutions, you can use AWS Gateway Load Balancer or do a trick with Elastic Network Interface reattachment. And I'm going to show you examples of both of these. We'll start off with the ENI reattachment. So in our scenario, we have a source EC2 instance on the left, some destination out on the internet. We have an instance A that might be a firewall. That has an Elastic Network Interface, ENIX. And then we configure a static route saying, if you're going to internet, go via ENIX. And then from the instance after inspection, you're going to the destination. Now, if that instance fails, it's on you to detect that it's failed. It's on you to provision a second instance. And then it's on you to do the API calls to migrate the Elastic Network Interface to the instance that's active. During that time, the traffic is getting black-holed, and effectively, you have an outage for this flow. Pro tip here is detaching and reattaching an Elastic Network Interface is a control plane operation, so it's an asynchronous API call. We normally don't recommend using API calls when you're doing an outage scenario, so data plane failover is the best. So you can see here straight away that this is not an ideal model. A better way to deal with resilience would be to use Gateway Load Balancer. And the way that Gateway Load Balancer appears inside of your VPC is as a Gateway Load Balancer endpoint, effectively a network interface that then maps to a Gateway Load Balancer itself. The way to think about a Gateway Load Balancer is like a load balancing router. So it's different from other load balancers, which are proxies, so they terminate connections. With Gateway Load Balancer, it's like a router. You route traffic to it, and then it can distribute traffic to different network functions, again, usually firewalls. So this time we're configuring a default route out from our source, setting up the Gateway Load Balancer endpoint as the destination, and then traffic is going to go and pick one of the firewalls. So that's on the Gateway Load Balancer to hash the flow and make sure that the right firewall is picked, both outbound and then return direction. So you don't have to worry about symmetric traffic flows. And then finally, you're getting to the destination. Now, if instance A fails, Gateway Load Balancer does health checks, so automatically realize that instance A failed and start moving existing new flows to instance B. If you need existing flows that were on instance A to be moved to instance B or C, you can enable that in the configuration options on the load balancer. So if we compare the two side by side, you can immediately see that the way to manage your network functions on AWS is through using a Gateway Load Balancer. Detects your failure automatically moves traffic to next appliance, and then it does all of this on the data plane without you having to make any control plane changes. Okay, so let's move out of our PC and start connecting to things outside. So the first thing we're going to do is connect it to a data center. So this is out somewhere on premise. It will have a router and a couple of networks, IPv4 and IPv6. We simplified our VPC, so now it's just a single subnet. And then to be able to connect back to on-premise over AWS Direct Connect, which is dedicated fiber that allows you to connect to our backbone, you need to provision a virtual private gateway, VGW. A VGW will have an ASN. That's an autonomous system number. This is related to BGP. You can think about ASNs as unique identifiers of every network. So every component will be provisioning has to have its own unique ASN. So we have a VGW. We then provision a Direct Connect gateway. So you will often see us show Direct Connect gateway as a component, as a device in the logical configuration. It is not. You can think about the Direct Connect gateway effectively as like a logical VRF or network capability that allows you to connect between multiple regions on AWS and different locations where Direct Connect is provisioned globally. And then from Direct Connect, we're creating a logical interface back to on-premise using a private virtual interface. Ultimately, the private VIF is just a VLAN running BGP on top, so there will be an eBGP session exchanging routing information between the Direct Connect gateway and the on-prem router. By the way, what I'm not showing here is the physical connectivity. So I haven't showed you the physical cable, the connection to AWS, the location. That's something that Ankit is going to show you in the second half of the session. So we're purely focusing on the logical right now. So if we look at the route table of the subnet A, we can see that we have an option to propagate routes that the VGW learns dynamically into the subnet route table. So you don't have to go in and statically configure those. You can automatically propagate those dynamic routes into your VPC route table. So now the VPC knows how to get back to your on-premise networks. On the other side, this is a route table of your device. So it's showing the network you're going to, the next hop on how to get there, and then the path will show you the autonomous system numbers that it's seeing. So you can see here that to get back to on-premise, to get back to the VPC, you can see both V6 and V4 networks, and the next hop is the Direct Connect interface. But we can see the ASN of the Direct Connect gateway. So Direct Connect gateway in this scenario hides the ASN of the VGW, and you will not see the VGW ASN in the path. Another tip here is that if you, by default, connect a VPC to a VGW to a DX gateway, all of the VPC CIDRs will be advertised to on-premise. You have the option to filter those at the VGW DX gateway level. And finally, I'll be repeating that one a lot. This is not a highly available deployment. I'm just showing an example of a logical connectivity. Ankit has detailed view on how to make this highly available on the Direct Connect side. Another option to connect your VPC would be using IPsec side-to-side VPN. That's a managed VPN. For a single VPN connection, you get 2 tunnels. Each tunnel is capable of doing around 1.2 gigabits a second. With a VGW, you end up using only one of those tunnels. You still have the option to set up BGP to exchange routing information. And then from the VPC perspective, not much has changed. It's still the VGW injecting routes into the subnet. So you don't know from a subnet perspective where do those routes come from. And then on the route table on the router, there's a small change. The ASN that we see in the path is that of the VGW because we no longer have a DX gateway in the middle. Now, a tip here is that it's optional that you can configure dynamic or static VPNs. Our recommendation would be to use dynamic routing for your VPNs to make your things highly available. Okay, so what's going to happen if a VGW has 2 connections? It has a VPN tunnel and a Direct Connect connection. So from your perspective, so you're controlling the router connecting to those constructs, so you can decide the path that the traffic is going to take. So if you prefer Direct Connect, you will prefer Direct Connect. Now, from a VPC perspective, we need to look at the documentation and see what is going to be the preference. And you can see here that the order of preference, other than static routes and longest prefix match, which is the more granular route, we will prefer BGP, Direct Connect BGP routes over VPN BGP routes. So traffic is going to flow over the DX gateway path. Again, you might think that a VPN as a backup to Direct Connect in this scenario is a good idea. We would recommend that for production level deployments, it should be Direct Connect as a backup for another Direct Connect rather than a VPN connection. Now let's talk about failover. So with static routing, we had to do some trickery to figure out what's going to happen if the next hop fails. With dynamic routing, it's a lot easier. Like BGP has an inbuilt mechanism where it will send keep alive every 30 seconds. And then if 3 keep alives fail, we will consider the connection as down. But the failure detection in this mode is going to take you 90 seconds. So that's quite a long time. To improve that, you can enable bidirectional forwarding detection, BFD. So that will send BFD packets within 300 milliseconds. So allow you to detect that there was a failure on the link within 1 second. Now, the pro tip here is this only works on Direct Connect, and then this only works if you're failing over to a Direct Connect connection. So if you're using BFD, you need to do it on Direct Connect, and you need to have another Direct Connect to fail over to. All right, let's expand our routing scenarios. So now we have a single region, but multiple VPCs. For that connectivity, we're going to use AWS Transit Gateway. Transit Gateway, think about it as a logical regional router. It can have 1 or more route tables. When you connect it to the VPC, you're creating these attachments. the way to think about them is like router interfaces, and then you associate these attachments with a particular route table. And that association defines what's going to happen with the traffic coming in from the VPC. So we create the attachment, land them on the route table. With Transit Gateway, we also have the option to automatically propagate VPC routes to the route table. So we do that, and then if I'm looking from the perspective of the route table, I know how to get to all the VPCs, V4 as well as V6 ranges. On the VPC side, I can configure a default route to say I want all traffic to go to the Transit Gateway, or I can create like an aggregate, maybe 10/8, that sends all the traffic to the TGW. And the tip here is to keep your routing inside of a VPC simple. Put the complexity on the Transit Gateway or Cloud one, which Ankit's going to show you in a second. But routing in the VPC should be as simple as possible. You don't want to make that too complex. Now, Transit Gateway also allows you to aggregate hybrid connectivity back to on-premise. Just be aware that there's an additional processing charge when traffic is going through the Transit Gateway, so check our pricing pages. You can use IPsec VPN to connect your Transit Gateway back to on-premise. The benefit over connecting to a VGW is that you can create multiple IPsec tunnels and distribute your traffic across them. So if you remember, a single tunnel can do 1.2 gigabits a second. Now you can add multiple tunnels, maybe 10 tunnels, and get more than 10 gigs over VPN. There's still a BGP session, and then that BGP session is used to add routes into the Transit Gateway route table. So we know how to get back to on-premise. In the other direction, we will see routes to the first VPC that I'm showing you, as well as all the other VPCs, and they're coming from the Transit Gateway autonomous system number. Pro tip here, if you need to connect to V6 as well as V4 ranges, you will need to create multiple VPN tunnels, separate for V4 and separate for V6. Another option is to use software-defined wide area networks to connect back to on-premise. For that, you would need to bring your favorite third-party vendor of your choice, deploy their headends inside of AWS as EC2 appliances, inside a VPC, connect that VPC to the Transit Gateway, and then on top of that, create connect attachments. We call them connect attachments. Ultimately, they're GRE tunnels. GRE tunnels is just another tunneling protocol. It allows you to get up to 5 gigabits a second, so it's a little bit faster than IPsec, but it doesn't provide encryption. On top of those tunnels, we also have eBGP, exchanging routing information between Transit Gateway and the SD-WAN headends. And then from there, the SD-WAN headends connect to the rest of the SD-WAN network and then back to your data center, as well as branches, wherever else you need to go. So in the route table, we can see that next hop for the on-premise routes is the connect attachment. And then on-premise, we can see that the routes back to the VPCs are through the SD-WAN, and then finally through the Transit Gateway. Now, SD-WAN does support iBGP as well as eBGP. Our recommendation is to use eBGP just for simplicity's sake and keeping things consistent. Finally, Direct Connect. We can also connect Transit Gateway over Direct Connect. We'll use a Direct Connect gateway and then create a virtual interface. This time it's a transit virtual interface. It also runs BGP. And the same way, we're getting all of the routing information dynamically propagated into the VPC. On your on-premise router, you'll notice that we'll see the routes that the TGW originates. So instead of those routes being dynamically advertised, you have to go in and manually configure the routes you want Transit Gateway to originate. And the limit of those routes is 200. So if you have 300 VPCs, you have to be able to aggregate those VPCs to maximum of 200 routes. Okay, so what happens if you have multiple paths here? Which one is going to be preferred? And which one you will prefer from on-premise? So that last one is easy to solve. Again, your router, you control the logic, so you can decide how the traffic is going to flow. For the Transit Gateway, we have a route evaluation order in our documentation, so you can check, okay, if the route is more specific, that's going to be preferred. In this case, we have the same routes, so we're going to prefer the Direct Connect Gateway propagated routes over anything else. So traffic is going to use DX. Now, the pro tip here is in the other direction, make sure you align your logic to keep traffic symmetric. So if you know that direct connect is preferred, prefer direct connect in the opposite direction. Now, if direct connect fails for some reason, the next available connectivity option is TGW connect attachments. Now, those will take over. So even though you can't see them in the routing table because that's just a forwarding information base, they're there, and they will take over if the primary route disappears. And then finally, if for some reason SD-WAN has an issue, traffic will flip to using IPsec VPN. Okay, let's add some complexity. So let's add inspection to the mix. So in this scenario, we want to add inspection between VPCs and on-premise. And to make it work, we will create multiple route tables. We will have a route table for the VPCs, and we will have a route table for hybrid connectivity, each one governing what happens to traffic coming in from respective attachments. We will then create an inspection VPC, attach it to a transit gateway, and then land it on its own route table. You'll notice that the attachment has appliance mode enabled. That's making sure that traffic passing through the transit gateway and going up to the attachment is going to stick to the same AZ. Now, from a routing perspective, in the VPC route table, we're pushing all the traffic that would normally be destined to on-premise using static routes up to the inspection VPC. After inspection, traffic will be using the route table inspection where we have all of our routes propagated. That's clean traffic. We can have all of the routes in there. In the opposite direction, the hybrid route table has a static route pushing traffic back up into the inspection VPC. And then we can configure static routes for all individual VPCs or create an aggregate route in there. Whatever we create will be advertised back to on-premise. Okay, so traffic can get back in, hits the inspection VPC, and after inspection gets to our VPCs. So moving on to adding multiple regions. So we know how a single region looks like. Adding a second region, pretty simple. We deploy the same transit gateway and a bunch of VPCs in another region, and then we can route our traffic between VPCs in that region. If we need traffic to communicate cross-regionally, we need to create transit gateway peerings between any combination of regions that we have. Those transit gateway peerings only support static routing today, so you need to create static routes to define what is on the other side of that peering. So even though this is static routing, the tip here is when you create transit gateways, give them unique ASNs, because once dynamic routing might be available at some point, that's going to help you. If we want to look at how inspection looks like, so say we want to inspect traffic between region 1 and region 2, we can follow the same pattern that we did with IPsec. And I'm not going to go through every single individual route table. Just going to give you an overview that traffic should be inspected in both regions. It's theoretically possible to make it work such that only one region would be used, but it's extremely complicated, and the more regions you add, the more impossible this task gets. So this is what you need to do. I'm going to quickly browse through it. But these are all the routes that you would need to configure to make this work, to just do inspection between regions. This doesn't even cover inspection within a single region if you have different types and families of VPCs. So there's a lot of configuration required here, just for 2 regions. You configured 6 different static routes, and that's keeping things simple, and then you have to create multiple route tables. At this point, I'm going to hand off to Ankit, who will show you how to do this global deployment, including inspection, with AWS Cloud One.
Can you folks hear me? Awesome. So folks, in the second half, we're going to be talking about specifically multi-region scenarios. We'll also share some pro tips on the way. And talking of anybody keeping track of how many pro tips we have shared thus far? 6? I think it's more than 10. OK, we'll summarize at the end with the total amount. So the first scenario that we'll talk about is providing connectivity to multiple VPCs using AWS Cloud WAN. AWS Cloud WAN is a service that allows you to create multi-region AWS networks within minutes. So first, let's talk about some of the constructs of Cloud WAN. The first one is CNE, or a Core Network Edge. This is a regional construct, and it is completely managed by AWS. This is the entity that actually pushes packets in and out. And under the hood, it looks and feels a lot like a transit gateway. The net benefit over a transit gateway is that you also get a full mesh eBGP peering that is, again, completely provided and managed by AWS. And this full mesh eBGP peering allows you to get dynamic routing within the same region or across multiple regions. The second construct is a segment. Think of a segment as a global routing domain or a global VRF or a global routing table even. These are global by default. So in this case, I'm showing 3 segments: development, test, and production, and each segment spans 3 separate regions. Now, even though segments are global by nature, they all have a regional routing view in that each segment will have a regional routing table too. This will become interesting as we start diving into the packet walks. Any attachments that you may have will get associated with segments. So if we expand this diagram and start adding VPCs, each VPC will have an attachment that is associated with one of the segments. Now, the final Cloud1 construct that we'll speak about is policy, which is a JSON document. And here's a snippet of how it would look like. This is a snippet that shows how you would define your 3 segments. Now, this JSON document governs your entire global networking policy. This allows you to express your intent in that how many regions should your deployment be present in, what are the attachment policies, as in which attachment should land into which segment, and how you can influence traffic or your individual routing flows. We'll dive into those details into the packet walk section. So with this base knowledge, let's go into the first use case, which is providing inter-region same segment routing across VPCs. So in this case, you have 2 VPCs in different regions, both associated with the dev segment. Now we spoke about regional routing views of the segments. So this dev segment will have a routing table in region 1. Over here, you would see region 1's VPC siders, which are expected. But additionally, you will also see region 2's VPC siders. And this is the propagated route that allows you to send traffic from region 1 to region 2. Similarly, you will have a corresponding route in dev segments routing table in region 2 as well. And these 2 highlighted routes will ensure that you have bidirectional communication without configuring any static routes. So if we expand this scenario a little bit and we start talking about VPCs across different segments, the diagram looks a lot like this. Now you have dev VPC on the left and a test VPC on the right-hand side in different regions. At the top, you have your dev segments routing tables, and as expected, you only see the dev VPC siders. At the bottom, you have your test segments routing tables, and you only see the test VPC siders. Now, your requirement is to provide connectivity between these 2 segments, or between VPCs that are connected into these segments. You do this using the Cloud1 policy. You would define a segment action where you would say, I want to share all of my attachment routes between the dev and the test segments. So going forward, we'll have this pink or purple underlined text, which would be the name of the segments. Now, when you execute this policy, new routes will start showing up in your routing tables. And these are the new routes. So if you dive into the dev segments routing table, you will now start seeing the siders for test VPC siders. And at the bottom, you will start seeing dev VPC siders in the test segment routing tables. And this is the NET mechanism by which you get multi-region dynamic connectivity using AWS Cloud1 across different segments. Now, key thing to keep in mind is, again, 0 static routes needed. There are some pro tips as well. Firstly, sharing routes works bidirectionally. So in this case, you had 2 segments. When you share routes, each of those segments see all of each other's as routes. Secondly, sharing routes is non-transitive. So if you were to create a 3rd segment and share it with, let's say, the test segment, then that 3rd segment will only see the test segment's routes. Now let's expand this further and let's start inserting firewalls and start inserting inline traffic appliances. So for your use case, you again have the dev VPC on the left, test VPC on the right-hand side. You need your regional firewalling stacks. Now these firewalling stacks get associated with a new kind of segment called a network functions group, or an NFG. This is an AWS managed segment, and the routing within this segment is completely orchestrated and managed by AWS. That said, you still get visibility into the routes in case you want to check out what routes live there. So your inspection VPCs get associated with the NFG. Let's bring up the routing tables. At the top, as always, we have the dev segments routing table. At the bottom, we got the test segments routing table. And now your requirement has grown. Instead of providing direct connectivity between these segments, now you want to start inserting firewalls. So this is orthogonal to the previous use case. So in this case, we have disabled route sharing. Let's look at the policy actions that you would need to define to insert this firewall. You will say that whenever traffic originates in the dev segment and wants to go to the test segment, send all this traffic via a network functions group called an NFG. And that's it. Again, takeaway is 0 static routes needed. Now, earlier you heard Tom mention about using transit gateway for multi-region connectivity with inspection. And with a transit gateway, it's a best practice to do dual firewalling. That is performing firewalling in each of the regions. But with Cloud WAN, you get to choose whether you want to perform single firewalling or double firewalling. You do that by using this knob called as mode. So single hop is the mode that defines that you only want to perform firewalling in one region. You can either provide the name of the region that you want to perform the firewalling in. If you don't, then AWS will deterministically pick one region for you. So let's dive into the packet walk. Let's go back to the scenario. Since we are using single hop, let's get rid of one of the firewalling stacks. So there may be potentially some cost savings here as well. When you execute the policy, new routes appear. So let's look at the dev segments routes. Now it sees the test VPC siders. And the next hop is that of the inspection VPC. This is the route that sends traffic from the dev VPC into the firewall VPC. Firewall performs its firewalling. And side note here is you need appliance mode enabled on the VPC attachment that goes towards the inspection VPC. That will keep your traffic symmetric. Now the return traffic from the firewalls will be looked up in the network functions groups routing table. This is again managed by AWS. The routes know that traffic must be delivered to the second region, so the traffic goes to the CNE in the second region. Now again, this is looked up in the NFG's routing table, and we know the traffic must be delivered to the test VPC. This completes one side of the flow. For the return traffic, the lookup is done in the test segments routing table at the bottom. Here, you will see a route for the dev VPC siders, and the next hop is again the inspection VPC. This route takes the traffic back to the same firewall VPC. Since you have appliance mode enabled, traffic is symmetrically delivered to the same firewall appliance. The firewall becomes happy because it likes to see both sides of a flow. Firewalls performs its firewalling, sends the traffic back into the NFG, and the NFG understands that the traffic must be sent to the dev VPC. So this is the net packet walk for performing traffic inspection along with Cloud WAN with this new feature that's called service insertion. It was released earlier this year. For the sake of completion, another route is added, but we didn't consider this route for this traffic flow. Now, what are the pro tips? Firstly, sharing routes and send via actions are mutually exclusive. You would share routes when you want direct connectivity. You would use send via when you would want to insert an inline appliance. Secondly, whenever you're using single hop, make sure that you define which regions firewalls should be used. Because if you don't, AWS will deterministically pick one region, and then there may be the risk of overwhelming that region's firewalls. And again, a takeaway is you can stand this entire thing up across multiple regions with 0 static routes. So in the last 15-20 minutes, you heard a lot about how you can use Transit Gateway and Cloud WAN for creating the same use case. So here is a comparison slide. I won't go into all of the details, but I'll pause here for 5 seconds in case you all want to take a picture. 4, 5. All right. So now we'll change gears. We'll start talking about hybrid multi-region networking scenarios, specifically over Direct Connect. And again, as Tom mentioned, these are some hand-picked scenarios that we have chosen to present in this session based on our conversation with customers. Now let's talk about Direct Connect resiliency first. You saw this diagram earlier with an AWS deployment on the left-hand side, Direct Connects in the middle, and your data center on the right-hand side. First, let's expand this to multiple regions. Let's start associating the Direct Connect gateway with multiple transit gateways, and behind each transit gateway, you have your VPCs connected into it. When it comes to the resiliency, it's critical to understand what happens under the hood, under that dotted line. So let's start demystifying that. So when you procure Direct Connect, you get a physical fiber connectivity between an AWS router and a customer router within a Direct Connect location. Once you have this in place, you start creating your virtual interfaces, a transit virtual interface in this case. And that is a combination of a VLAN and a BGP peering. Once BGP is up, you can start exchanging routes. As for the last mile connectivity, you can either bring your dark fiber or work with a partner to provide connectivity to the Direct Connect location. Now, while this works, you're susceptible to a single point of failure, which is the link between the AWS router and the customer router. And as a matter of fact, we constantly run maintenance on our AWS routers that we communicate in advance. So with a deployment like this, it's guaranteed that you will have a downtime at some point or the other. So to protect against that, you can replicate this within the same Direct Connect location, procure another circuit, create a transit WIF, and then it's best practice to terminate the last mile connectivity on a different customer router. With this, you're again susceptible to the corner case, unlikely scenario in which case the Direct Connect location itself fails. So to protect against that, you can replicate this deployment across another Direct Connect location, get 2 links, create 2 more WIFs, and then terminate the last mile connectivity on different customer routers. Now with this, you're protected against a link failure, a router failure, and also a Direct Connect location failure. Now the question comes up, after you make all this investment in the hardware, in the Direct Connect connections, is there a pro tip when it comes to creating resiliency configuration-wise? So the pro tip is to advertise the same prefix over multiple WIFs so that you have logical redundancy in place as well. Now this scenario where we have 4 Direct Connect connections across 2 locations will be our baseline for the rest of the routing scenarios that we discuss. And another thing to keep in mind is that each Direct Connect location has an associated AWS region. And we'll talk about that information as we start diving into load balancing. So with this baseline, let's talk about the first use case, which is on-prem to S3 access. From a deployment perspective, this is our baseline, 4 connections across 2 locations. And that the orange line is actually a public WIF or a public virtual interface, which is also a BGP peering. The use case is providing bidirectional connectivity from on-prem to S3 buckets hosted inside of multiple regions. So since public WIF also works on top of BGP, let's see what kind of route exchanges happen here. So once the BGP session is up, you will start seeing all of AWS's public prefixes, including any bring your own IP addresses that you may have brought in. When you look at the routing tables of your on-prem routers, you will see all public prefixes. The next hop would be the interface facing Direct Connect. And the path, the AS path will include 7224 because that's Amazon's public ASN. After that, you can start advertising your public prefixes so that AWS can reach back to you. And the pro tip here is to treat a public WIF just like any other internet-facing connection. So if you have specific security measures in place for public connections, we recommend you apply those to a public WIF as well. So with this, let's go back to the scenario. Once BGP is up, you see AWS's public prefixes. You start advertising your public prefixes to us. And the pro tip here is load balancing with public WIF is only allowed in the same associated region, which means in this case, you can load balance across the 2 locations if they are associated with the same AWS region. And you can go through the documentation to understand whether the Direct Connect location where you have connections, which AWS region is that associated with. Now let's dive into private connectivity. So earlier we spoke about how you can provide connectivity into public resources like S3 buckets. This time we'll extend connectivity from your on-prem data centers to your VPCs. So for this, let's go back to the baseline scenario. You got 3 regions. You got a regional transit gateway in each of the regions associated with a Direct Connect gateway, 4 Direct Connect connections across 2 locations, and then you have your data centers. So with this, as you heard Tom in the first part, on the association between transit gateway and Direct Connect gateway, you need to configure allowed prefixes. The limit over there is 200 prefixes per association. And the pro tip here is overlaps are not allowed in the allowed prefixes configuration. So if you have 3 different transit gateways, as you're seeing on the screen, you must have unique prefixes originating out of each association. When you look at your on-prem routers, you will see the transit gateway originated routes. Next hop is the direct connect facing interface. And the path will only include the ASN of the direct connect gateway. Now let's change the game. Let's see how you would do this with Cloud WAN instead. So everything remains the same. The only change that we make is instead of regional transit gateways, now you have a global Cloud WAN deployment. And each CNE has an association back to the direct connect gateway. Now in this case, there are 2 benefits that you leverage as compared to a transit gateway based deployment. The first one is instead of configuring allowed prefixes for every association, you automatically get dynamic routing in both the directions up to a maximum of 5,000 routes. So you get dynamic routing and the limits are increased. The second benefit is this time with Cloud WAN, Direct Connect Gateway does not hide the CNE's ASN. So when you look at your on-prem routers, you will see the CNE's ASN as well as the Direct Connect Gateway's ASN in the AS path. So this provides you with a net visibility benefit in case you're debugging or in case you want to know where a route originated from. So now with this baseline of a global deployment with AWS Cloud WAN and Direct Connect Gateway and Direct Connect connections, let's see how you can influence traffic. So in this case, let's say you always want to prioritize the top link when it comes to sending traffic from AWS back to on-prem. The easiest way of doing that is by using more specific routing. So you can advertise, let's say, a /24 from the top link and a /16 from the rest of the links. And as you heard in the previous section, more specific routing always wins. So this would ensure that the top link is always prioritized. But often it's not possible to send more specific routes from each of the connections. And we work with customers who can only advertise a summary from each of the links. So in that case, you can use BGP attributes like AS path prepending and local preference to influence traffic from AWS to on-prem. And again, this is important because in the other direction, you can always use BGP attributes on your own routers for influencing traffic from on-prem to AWS. So diving in, the first one is AS path prepending. Let's look at the scenario first. You have a network A at the top, and you got an AWS router at the bottom that has 2 ways to reach this network. And you want to influence, use the BGP attributes to prioritize one path over the other. So with the AS path prepending, you can have router 1 advertise the prefix with an AS path length of 1. And on router 2, you can advertise the same prefix with AS path length of 2. Now, when you look at the routing table of this router, it will perceive that the route through router 1 has lesser hops, and it will always prioritize that. So this is one mechanism. The second mechanism of prioritizing routes or influencing traffic paths is by using local preference. So in the Direct Connect world, you have BGP communities that translate into local preference. So the scenario remains the same. You have network A, you have AWS router at the bottom that has 2 paths, and you want to pick one path over the other. So on the left-hand side from router 1, you advertise the prefix with a community of 7100, and this translates into a local preference value of low. On the other side, you advertise the same prefix with a BGP community tag of 7300 that translates into a local preference of high. And when you look at the BGP table, this AWS router will always prefer the route on the right-hand side because of the higher local preference. You can look at AWS documentation to see the exact string that you need to use in the BGP community. All right, so now that you have 2 mechanisms to influence paths from AWS to on-prem, the question is when to use which. So while there are various permutations and combinations of using these, here is a simple mental model that you can use. Use AS path prepending when you want to influence paths in the same Direct Connect location. Use local preference when you want to influence paths across multiple Direct Connect locations. And here is a pro tip. In case you configure both of them, local preference will always win over AS path prepending. All right. So let's go back to our scenario and let's have a traffic engineering exercise. So let's start with numbering the links first. You have 4 direct connect connections, and your high-level requirement is that you must always prioritize direct connect location 1 over direct connect location 2. Now we are talking about traffic engineering across locations, so you can use local preference here. You can advertise the same summary routes with a community of 7300 from the top 2 connections. That translates into a high local preference. You can advertise the same prefix with a low local preference or community of 7100 at the bottom. This takes care of ensuring that direct connect location 1 is always prioritized. But to make it more spicy, you can also say that, okay, between links 1 and 2, 1 should always be preferred. Now we are talking about traffic engineering within the same location. This is where you can use AS path or AS path prepending. So from the top link, link 1, you advertise it with an AS path length of 1, and you use AS path prepending on the second link. So with this, between links 1 and 2, link 1 will always be used. In case link 1 is down, link 2 will be used. All right, so that was a lot of information, folks. Let's look at the summary. So we started off by looking at the routing building blocks that AWS offers. Then we started looking at routing scenarios. We started off with a single VPC where Tom spoke about how the VPC subnets routing tables work, how you can create static routes, propagated routes, and dynamic routes. Then we started expanding. We connected multiple VPCs within a same region. We started inserting inline firewalls. Then we expanded it to multiple VPCs across multiple regions. And then finally, we ended with advanced hybrid connectivity, where we spoke about multi-region and multi-direct connect related scenarios. And I think we covered 22 pro tips. So with that, Tom and I would like to thank you for attending and giving us your attention. In this session, we tried a couple of new things, specifically the pro tips. So if you like it, please use your app to give us feedback. And any feedback for improvement is also welcome. Thanks, everyone.